Good evening, ma'am. Is everything clear, ma'am? Audio?
Yes, sir.
Okay, ma'am. Thank you. Thank you.
Sir, you can start, sir.
Yes, ma'am. Yes, ma'am. Good evening, students. So, first of all, I would like to convey my Independence Day wishes to all of you. We are celebrating the 75th Independence Day today, and I would like to convey my wishes to all of you. So, for the past few weeks, we were discussing the various concepts in electrostatics, and today we are going to discuss something regarding the conductors in an electrostatic field. So that concept we are going to discuss now. So when you place conductors in an electrostatic field, what will happen actually? Okay, so this is what we are going to discuss today. And I hope you all are able to see my screen. Are you able to see my screen, students?
Yes, sir.
Yeah, thank you. Thank you so much for your response. So whenever you place a conductor in an electrostatic field, what happens actually? So when you place a conductor in an electrostatic field, you know very well that the conductors have a lot of free electrons, and whenever you place conductors in an electrostatic field, what happens is that the charges or the free electrons inside the conductor, they start moving. Okay, they start moving due to the presence of an external electric field or electrostatic field, and due to that, what will happen is uh, there will be an induced electric field inside the conductor. Okay, due to the channeling of the various charges or the various free electrons inside a conductor, there will be some induced electric field inside the conductor, and what will happen in course of time? Okay, so as long as you keep that conductor in an external electrostatic field, the induced electric field inside the conductor starts growing, and it will oppose the external electric field, and after a period of time, what will happen is that the electric field induced inside the conductor actually cancels out the electric field outside. Okay, so whatever electric field has been induced inside, whatever electrostatic field has been given by the external supply, that is actually when you keep the conductor in an external electrostatic field. Okay, so what will happen is that, just 1 second. So let me come back now. Yeah, so let us continue now. So now, whatever the electric field induced inside the conductor, okay, so that electric field actually opposes the electric field from outside. So under this induced electric field grows in such a way that the total electric field inside the conductor becomes zero. Okay, so this is what happens when you place conductors in an electrostatic field. So this is the first point you need to understand carefully. So whenever you keep conductor in an external electrostatic field, the field inside the conductor becomes zero. And the second one is the charges. Okay, it reside only on the surface of a conductor. Okay, surface of the conductor. So the total charges inside the conductor, it will be zero. Okay, so the electric field is also zero, and the charges won't be inside the conductor. Okay, this is a direct consequence of Gauss law. So you know very well, integral E dot ds is equal to 1 by epsilon naught into q. That is the total charge enclosed. Okay. So in the inside of the conductor or the interior of the conductor, okay, you won't be having any electric field. That has been clearly mentioned in the first point. Okay. So so since the electric field inside the conductor is zero, okay, when you take the integral of this electric field with the surface area at any point inside the conductor, since the electric field is zero, the integral vanishes. So that means on the right hand side of the equation of the Gauss law, okay, you know, you all know very well about the Gauss law. So that is, so let me write here. So you all know very well about the Gauss law. That is integral E dot ds. Okay, integral E dot ds, that will be equal to 1 by epsilon naught times the net charge. Okay, enclosed within the surface. So in the interior of the conductor, you know very well that the electric field is actually zero. Okay, inside the conductor is zero. So this is why this integral on the right hand side of this equation, this will become zero, and due to that fact, actually on the right hand side the net charge will become zero. Okay, because the 1 by epsilon naught can't be zero because epsilon naught is a constant, so that can't be zero. So the electric field inside a conductor is zero. That means the net charge inside the conductor is zero, and the charges can reside only on the surface of the conductor. Okay. The third point is, you all know very well this relation E equal to minus dV by dr. Okay, the relation between electric field or electrostatic field and the potential. So, according to this relation, E equal to 0 inside a conductor. So, E equal to 0 means from this equation what we can understand is, so here I am writing E equal to minus dV by dr equal to 0. Okay. So E equal to minus dV by dr equal to 0. So here you are getting minus dV by dr equal to 0. So whenever you differentiate a particular quantity and you get 0, what is the meaning of that? Actually, that quantity is a constant one. So here you have dV by dr equal to 0. That means the potential is a constant quantity. So the electric potential is actually constant or 0 anywhere inside the conductor. That means inside the conductor and of course outside the conductor also, you are getting equipotential regions. Equipotential means we have already discussed that concept actually. The potential value is same everywhere. So since E equal to minus dV by dr, the electric potential, the electric field is actually 0. So the electric potential is either constant or 0 anywhere inside the conductor. So in an electrostatic field, there will be equipotential region. Okay. So this is the next point you need to understand clearly. And the next point is the electric field lines are actually perpendicular to the conducting surface. Okay. So whatever surface you take, okay, whatever surface of the conductor you take, so let it be in a irregular shape. The electric field lines always they are perpendicular to the surface of the conductor. Whether it is going outside or whether the field lines are coming inside, the field lines are always perpendicular to the conducting surface. Okay, this is the surface of the conductor, and the field lines are actually perpendicular. Okay, so this is the next point you need to understand. Right. So then I will be moving on to the surface charge density of a charged conductor. Okay, so I have to clear these annotations, then only we will be able to see the other slides clearly. Okay, otherwise these annotations should be disturbing. So here you can see the next slide, the surface charge density of a charged conductor. So this concept is nothing but action of points. Okay, I hope you all might have studied about the action of points. So do you know anything about the action of points, students? Do you know anything about the action of points? Have you all studied anything regarding the action of points in your school? Students, action of points. Have anyone studied anything about this? Students, anyone? Action of points? Has anyone studied anything about that? You can tell whatever you know about that, no issues. Even if it is wrong, then it's also not a problem. So only point is you can give it a try. Okay. So has anyone studied anything about the action of points? Students, you can unmute yourself and you can talk during the class. Action of points, students. Ajay Sariel.
Sir, don't know, sir.
You don't know. Okay. Anyone else? The action of points. Okay. If you don't know about the action of points, let me ask you a general question. Do you know anything about the lightning conductors? The lightning conductors. Do you know anything about that? The lightning conductors, or have you ever heard of that word lightning conductors? Or lightning arresters?
Yes, sir.
Yeah, whatever you know about that, you can tell me, Ajay
Sir,
Sariel.
it's basically like a metal rod with an earth connection, sir, that is used to prevent lightning from striking any object like a house or a building or a
Yeah,
structure.
very good. Excellent, excellent. This is the purpose of lightning arrestor or lightning conductor, that is to protect the building or protect a particular apartment or anything. Okay, protect any building from lightning. They are actually using the lightning conductor. And what is the principle behind the lightning conductor is actually the action of points and electrostatic induction. So these two concepts are involved in the working of lightning conductor, and the action of points now we are going to discuss. Okay, now we are going to discuss the action of points. So whatever be the shape of the conductor, okay, the surface charge density is actually inversely proportional to the radius of curvature.
Sir,
Yes, tell me.
sir, are you sharing your screen, sir?
Yes, I am. Yeah, please wait. I think the sharing has been stopped here. So let me start sharing once again. I think now the screen is visible to you, right? Think,
So no, sir.
yeah, wait. I think there's some problem. Okay. I will close the PPT once again and then I will reopen it so that you will be able to see the PPT. Okay. Now I think you will be able to see the PPT. Okay. Are you able to
Yes,
see
sir.
the screen? Ah, yes. Okay.
Yes, sir.
Okay. Okay. So the action of points we have been discussing right now. Okay. So the action of points means whatever the shape of the conductor. Okay. Whatever the shape of the conductor, the charge density or the surface charge density, it is inversely proportional to the radius of curvature. Okay. So let me draw a conductor here. This is the shape of the conductor, or even I can draw like this too. Okay? Like this. Okay. So whenever you give some charges to the conductor, what happens is the charges are less crowded at the point where the radius of curvature is more. But here at the sharp points, the density of charges will be more. This is called action of points. Okay. That means here the conductor is having least radius of curvature, so the charge density is more here. And when the radius of curvature is minimum, the charge density is more, and it is vice versa. That means the charges always tend to move towards the pointed or sharp ends, okay, of a charged conductor. So this is why a lightning conductor actually protects the building from lightning. Okay. So whenever you have a sharp edge like this, okay, a sharp edge or even like this. Okay. So whenever you have a sharp edge like this, then charges always tend to accumulate at the sharp edges. That means the surface charge density of a conductor is always inversely proportional to the radius of curvature. Okay. So this is what action of points is all about. So the surface charge density of a charged conductor is also the concept of action of points. Okay. So nothing new. You all might have studied these things. So this is what surface charge density of a charged conductor is all about. Okay. Right. Then the next thing is sharing of charges between conductors. Okay, sharing of charges between conductors. So here we are considering two hollow spherical shells, conducting hollow spherical shells, and we have a different radii for these conductors. Okay, so here you can see Q1 is the charge given to this spherical shell of radius R1. Okay, R1 means capital R suffix 1, that is the radius of this smaller spherical shell. Here we have given Q2 as the charge to the spherical shell. Here we have a bigger sphere. So for the bigger sphere, we are having the radius R2, and we have given the charge Q2, okay, to the bigger sphere. So since these spheres have different radii and different amount of charges, okay, so will they have the same potential or will they have different potentials? Both these spheres. Can anyone tell me? The radii and the charges of both these spheres are different. Will they both have the different?
So,
Yes, tell me.
so different potentials, sir.
Yes, they will have different potentials. Okay, those spherical shells or spherical conductors, they will be having the different potentials, right? So here you will be having V1 amount of potential. Okay, so here you will be having V1 amount of potential for this charged sphere, and here for this charged sphere you will be having V2. Okay, the potentials are not same, they are different actually. So now I am connecting both these conductors with the help of a wire. Okay, with the help of the wire. Now what will happen actually? When I connect both these conductors with the help of a wire, what will happen? Will there be any transfer of charges between these two spherical shells? Will there be any transfer of charges, students? You can try. I can.
Sir,
Yeah. Tell me.
sir, yes, sir, I think so. There will be a transfer of charge.
Why? What is the reason behind that? Can you just tell me? Your answer is correct.
Yes, sir, because the surface, sir, the charge densities are different, sir. So obviously the charge will go from, or there will be a sharing of the charge, and it will, so that it can balance out each other, sir.
Not only the charge densities are different, you have the different potentials, right? So
Yes, sir.
you are having the difference in potentials between these two spherical shells. So due to the difference in potentials, charges tend to move from higher potential region to the lower potential region. That means it will try to move from the sphere having the higher potential to the another sphere having the lower potential. How long will it take? How long will it happen actually? Right? So the transfer of charges actually takes place between the two spheres, but how long it will happen? It will happen till the potentials on both the spheres are actually same, or the potentials on both the spheres become equal. Okay, till that you will be having transfer of charges or sharing of charges on both these spheres. So this is what sharing of charges is all about, at least for this case. But generally, for not only for the spherical shells, for conductors having any shape, you can have transfer of charges or you can have sharing of charges. So between the conductors, as long as there are potential difference between the two conductors. So here also the sharing of charges will happen uh, till the potentials on both the spherical conductors become equal. Okay, so after the transfer is complete, you will be having the charges on both these conductors according to this relation, q1 by q2 equal to r1 by r2. Okay, so this relation is applicable in this case, and the ratio of the final surface charge density on both these spheres is sigma 1 by sigma 2 equal to r2 by r1. Okay, so you should not confuse both these relations. You can see here q1 by q2 equal to r1 by r2, the ratio of the final charges on both these conductors. And you should note that only the ratio, okay, q1 by q2, only the ratio is equal to r1 by r2, not q1 is equal to q2. Okay, it is not right. Actually the ratio of q1 and q2, it is equal to r1 by r2. Okay, so this is what the ratio of final charges is all about. And the ratio of the final surface charge densities, it is sigma 1 by sigma 2 equal to r2 by r1. Okay, so the ratio of the final surface charge density actually r2 by r1, sigma 1 by sigma 2 equal to r2 by r1. So this is how the sharing of charges happens between the two spherical shapes. Okay, right. So now I will be asking you just one or two simple questions based on the topics whatever we have studied. Okay, so now I will be asking you some one or two questions. Okay, for that I will be opening a whiteboard. I will be writing some questions on the whiteboard so that you can answer. Okay. I will be, please wait. Okay. Now I will be asking you one question. Okay. If a unit positive charge is taken from one point to another. Okay.
Excuse me, sir. Are you writing anything newly, sir?
Yes, ma'am. Are you able to see this? See this?
I'm not able to see that, sir, because the net charge on hydrogen atom, that question is coming here.
Okay. Okay. So actually, I have opened a new page. I thought it is visible to you, but please wait. Let me see. I will close this whiteboard and then I will open a new whiteboard so that there won't be any confusion. Now, can you see a blank whiteboard, students?
Yes, sir.
Yes, sir. The screen is blank.
Yes. So this now I will be writing on this screen, okay, so that it will be visible to you. Earlier, I was using the opening the same whiteboard and I am using a different page, but that was not visible to you. Now I am writing. Are you able to see this, students? I am writing on whiteboard. Are you able to
Yes,
see?
sir. Yes, sir. We can see, sir.
Okay. So if a unit charge is taken from one point to another, over an equipotential surface, then work done on the charge value. Okay, work done on the charge value. Work done on the charge is. So can anyone tell me what is the value of the work done here? If a unit charge is taken from one point to another over an equipotential surface, then work done on the charge is. Can anyone tell me what is the answer for this?
Sir, is it 0, sir?
0. 0, sir.
Yes. Why?
Sir, because there is the surface is equipotential, sir. So when you're moving a charge from one point to another point, there'll be no work done, sir.
Yes. Can you explain it on the basis of the mathematical equation or the mathematical formula? I think you two can write on the whiteboard, I think. Can you explain it on the basis of equation? Your answer is absolutely right. There is no doubt regarding that. But can you explain it on the basis of the equation? Can you tell me any equation to explain your answer? Okay, so let me write the equation for that. Work done equal to the charge multiplied by delta V. Delta V means the difference in potential, okay? Where delta V is actually the difference in potential. So here we are actually talking about equipotential surface. That means there won't be any difference in potential between the between any two points in the surface. So when you take an equipotential surface, there won't be any delta V. So delta V is 0. That's why the work done is also 0. Okay. So this is the reason for that. And this is how you need to understand the concept. Okay. Right. So now my next question I am writing here. So the surface of a conductor So what is the potential on the surface of the conductor at different points? Okay, at different points, what is the potential on the surface of a conductor? Potential on the surface of a conductor at different points. Will it be different or will it be same or will it be 0? Can anyone tell me potential on the surface of the conductor? Potential value. Will it be same for all points or will it be different for all the different points or will it be 0 actually?
Sir, in equipotential surface, sir.
Just on the surface of a conductor. I am talking on the surface of a conductor.
So,
Yes, tell me.
sir, it will be same for all points, sir.
Yes, your answer is right. Can you explain that? Why it is same? Because the surface of a conductor is actually, yes, tell me. It is equipotential. Okay?
Yes, sir.
Just now we have discussed that point. So it is equipotential. So potential on the surface of a conductor is same. Okay. Right. So now we have to discuss one more thing, that is polarization. Okay. Polarization we need to discuss. Polarization. So polarization means
Sir,
actually, yes, tell me.
sir, are you sharing a screen, sir?
Yes, I am sharing my screen. Are you able to see that? Oh, please.
Sir,
Please.
is it whiteboard, sir?
Yes, it is actually whiteboard.
Sir, I can't see, sir, what you're writing. That sum is
Okay,
only
the previous page were you able to see?
Yes, sir. Sir, I can see the sum, sir, but whatever you're writing now, I can't see.
Now,
sir.
okay. Are you able to see the whiteboard now?
Yes, sir. Yes,
Now.
sir.
Okay. So polarization. Polarization means the separation of charges. Okay, the separation of charges. So usually you are having two different types of molecules based on polarization, that is polar molecules and non-polar molecules. So can anyone tell me the difference between the polar and non-polar molecules?
So polar molecules are one in which there is a charge on each of the molecules, sir, and it attracts each other. So non-polar is when there is no charge, sir.
Actually, you can refine your answer. So polar molecules means usually the center of positive charges and the center of negative charges actually separated, okay, for the polar molecule. So in a polar molecule, there is a separation between center of positive charge and negative charge. Okay, so center of positive charge and negative charge are separated. That is actually the polar molecule. Center of positive charge and center of negative charge, they are actually separated. Okay. Center of positive charge is separated from center of negative charge. But in non-polar molecules, the center of positive charges actually coincides with the center of negative charges. So center of positive and negative charges are coinciding. Okay. So they are actually coinciding. So this is the difference between the polar and the non-polar molecules. So this means the polar molecules have their dipole moment, okay, even in the absence of external electric field. They have dipole moments for different molecules, but for non-polar molecules, you won't be having any dipole moment, okay. So these polar and non-polar molecules, they actually come under the category of dielectrics, actually. Dielectrics. Dielectrics are nothing but insulating substances, or they are non-conductors. Okay. So dielectrics are actually non-conductors. So dielectric means non-conductor. So polar and non-polar molecules are the two categories of the molecules which come under dielectric. So here you can see that in polar molecules, you will be having the center of positive charges and center of negative charges separated already. So they have their own dipole moment, and in non-polar molecules, since both are coinciding, you don't be having any permanent dipole moment in the absence of any external field. So since they are dielectrics, what will happen when you place them in an external electric field? Okay, so here you are having an external electric field, and here you are having a dielectric. Okay, you have an external dielectric field, and here you have an external electric field, and here you are having a dielectric. So due to this electric field, what will happen? Okay, so the separation of molecules happen for non-polar molecule. So minus and plus are separated due to the presence of the external electric field. So in the absence of electric field, what happens actually? So in the absence of electric field, as I have told you earlier, the center of positive charges and the center of negative charges actually they are coinciding. So the arrangement is like this. Okay, center of positive charges and center of negative charges are coinciding. That is, external electric field is 0 here. Okay, external electric field is 0. But here the external electric field is non-zero. So here you have separation of charges, and due to the separation of charges, you will be getting an induced electric field here. Okay, induced electric field. This is called induced because actually there is no electric field inside the dielectric. So due to the presence of this external electric field, you will be having induced charges and induced dipole moment also. So this induced electric field, what it will do? It actually opposes the external electric field. Okay, but the difference between conductors and these dielectrics is that As in case of conductors, okay, when you place the conductors on an external electric field, the field induced inside the conductor will actually grow until the point such that the electric field inside the conductor becomes zero. So I think you can catch my point. Actually, in the conductor, what will happen when you place the conductor in an external electric field? The field, induced field inside the conductor will grow in such a way that it will cancel the external electric field, so that the electric field inside the conductor becomes zero. Okay, the induced electric field in the conductor, it operates in such a way to nullify the external electric field, so that the net electric field inside a conductor will be zero for a conductor, in case of a conductor. But here they are dielectrics, and even within the dielectric you have a non-polar molecule here. So in the absence of external electric field, the positive and negative charges are coincided on each other, or coinciding on each other. When you place them in an external electric field, you can see that there is an induced electric field inside the dielectric, and this induced electric field actually opposes the external electric field, but it is not strong enough to nullify or to cancel the external electric field. It only reduces the external electric field. This is the difference between conductors in an external electric field and dielectrics in an external electric field. Okay, here the induced electric field cannot cancel the external electric field, but it can only reduce the value of the external electric field. Okay, so this is what non-polar molecules in non-polar dielectrics in an external electric field is all about. What about polar dielectrics? So in case of polar dielectrics, okay, actually you have charge separation without the external electric field also. So even though E equal to 0, you have a charge separation, but the orientation of these dipoles, okay, the orientation of these dipoles is in random direction in the absence of an external electric field. Okay, the orientation of the dipoles is like this, in a random direction. The plus minus I have actually shown here. Actually, they have the permanent dipoles, but they are oriented in different directions, or the orientation is random in the absence of an external electric field. Okay, due to thermal agitation. Thermal agitation means due to heat energy. Actually, the orientation of dipoles is disturbed and it is random. But in the presence of an external electric field, okay, that means when the external electric field is non-zero, the dipoles actually tend to orient like this, okay, such that there will be an induced electric field, and that electric field is actually opposing the external electric field. So this is same as that of a non-polar dielectric, but here only the alignment of dipoles is the main difference between the non-polar dielectrics and the polar dielectrics. Okay, so this is how you need to understand the polar and the non-polar dielectrics and the concept of polarization. And the polarization is actually given by capital P, and that is equal to alpha into E, right? Alpha is the polarizability of the molecule and E is the induced electric field. Okay, so this is the formula for polarization. So this is what dielectrics and the polarization is all about. Okay, I think you all understood the concept very well. So now I will be discussing one problem. Okay, I will be discussing one problem on the same screen. Based on the concepts of electrostatic potential we have discussed, now I will be discussing a problem. So the electron potential or the electric potential B as a function of distance x. That is, distance x means the distance is actually in meters, right? The distance is actually in meters is given by V equal to 5x squared plus 10x minus 9 volt. Okay, volt. So now my question is the value of electric field at x equal to 1 meter would be. Can you solve this problem and then tell me the answer? Can you solve this problem and tell me the answer? I have given you the electric potential as a function of distance, and I am asking you to find out the value of electric field at x equal to 1 meter. Students, you can solve and tell me the answer.
Sir, 6, sir.
What is the unit of that?
Meter, sir.
Not meter actually. Since I have asked you electric field, what is the unit for that? Unit for electric field. It is volt per meter. Okay, it is volt per meter. So the electric field, how you should calculate? So E equal to minus dV by dx. Okay. So minus of dV by dx means I have to differentiate. So d by dx of 5x squared plus 10x minus 9. Okay. So minus d by dx of, so let me write it here, 5x squared plus 10x minus 9. So when you differentiate it, you will be getting minus within the bracket 10x plus 10. Okay. So minus 10x. So within the bracket 10x plus 10 means you have to apply x actually. Okay, so 10x plus 10. So instead of x, you have to apply 1 meter. So here minus 10 into, instead of x, you have to apply 1 plus 10. So it will be minus 20 volt per meter. So this is the value of electric field at x equal to 1 meter. But some students told it is 6 volt per meter. I think so. So you should please check your calculation. Okay. So
Okay,
this is
sir.
how you need to solve that. Yes. Have you done any mistake in your calculation? Have you recognized that?
So we have done in direct way, sir. So
You have done it in direct way.
yes, sir. For an example, it's 5x square plus
Ah.
10x minus
Okay.
9. So
Okay.
in case of x, we have put it a 1 meter.
Okay. I
So
think
5.
you didn't go for differentiation, right?
No, sir.
Okay, you didn't go for differentiation. That's why you are getting the wrong answer, I think.
Yes, sir.
Is it so?
Yes, sir. Yes, sir.
Yes. So you should be careful with your calculations. Okay, students. So E equal to
Sir,
minus.
in every cases of finding the electric field, we have to apply the same formula. Vector E is equals to minus dV by dx.
Actually, whenever the potential is given as a function of these quantities, that is V is given as a function of x, y and z, or even x and y, or even x alone. Okay, whenever the potential is given as a function of x, y and z, or even it is simply x, simply y, or simply z, then you should go for this equation. That is negative gradient of the potential. Gradient means you have to go for differentiation of the potential. Okay. So whenever you have to find out the electric field, it is actually the negative gradient of potential, that is minus dV by dx. So the potential usually when it is given as a function of x, y and z, you have to apply the differentiation. Otherwise, you don't have to go for this formula. Okay.
Sir. Okay, sir. Thank you.
Yes. So today we discussed about the conductors in electrostatic field, that is inside a conductor, when it is placed in an electrostatic field, the electric field will be zero. Okay. So inside the conductor, the electric field will be zero, and the charges inside the conductor will be zero actually. Inside the conductor at the interior, so it is zero. And we have discussed about the action of points, that is the charge density is more where the radius of curvature is minimum. The charge density will be less when the radius of curvature is maximum. That is the inversely proportional relation. So all these things we discussed, and the sharing of charges between two conductors. It will happen in case of potential difference between the two conductors. So that case also we discussed today. Okay. All these things we discussed today, and we discussed about the polarization and dielectrics. Okay. So does anyone have any doubt?
No,
on the
sir.
Yeah.
No, sir.
Okay. Thank you, students. So we shall continue our discussion of electrostatics in our next class. Thank you so much for joining.
Thank you, sir.
So once again, happy Independence Day, sir.
Yeah. Thank you, students. Thank you. Same to you also.
Thank you, sir.
Thank you. Thank you.
Children, please join for biology class.